Okay, good. So our research paths never really intersected directly, but of course I did for many years admire Professor Salam from a distance and realised that many of his ideas had a very important indirect impact on condensed matter physics. And so I'd like to thank the organisers for inviting me to talk at this meeting. I'm going to tell you a little about the way in which Majorana fermions, which of course, as you all know, originated in the particle physics field, have recently become a hot topic in condensed matter physics. Some of you, I suspect, will know a great deal about this. Others will have heard things about it and perhaps not know the details. I will start off by giving you the standard picture. In fact, I'll probably spend 80% of this talk on the standard picture. But then in the last few minutes, I will try to give some reasons why I personally believe that the standard picture needs rather substantial correction. Okay, so incidentally, I should say this: the individual research I've been able to do in this connection was based in part on collaboration with my student, Yiro Lin. Sorry. I can use. Okay, I guess I can use the. Okay, fine. Okay, so as a reminder, I'm sure you don't need reminding of this, but Majorana fermions in particle physics are. A Majorana fermion is a fermionic particle, which is its own antiparticle, and therefore obeys this a rather unusual commutation relation. And it's known that such a particle has to be massless. Now, the question is, how can such a particle arise in condensed matter physics, where normally one assumes that there's no kind of particle-antiparticle symmetry? Well, they arise typically in the so-called mean field theory of superconductivity. And for the moment, let me just give you the general case. Imagine that we have a general non-relativistic Hamiltonian of a standard form which has a kinetic energy here and a one particle potential energy, which could perhaps be due to some kind of lattice or impurities or whatever, and then we have a four particle interaction in a rather general form here. Suppose now that we introduce the idea, which of course has a lot to do, obviously, with the work of Professor Salam, the notion of spontaneously broken U1 symmetry, the idea that we can treat the particle number, the total particle number, as not conserved. Then, in fact, we can write down an even parity, a ground state of the form here, where the sum here goes over all even values of n. And crudely speaking, this is the physical idea behind this is that you have Cooper pairs formed in your system, and it's often one often takes the approach that the number of these Cooper pairs, and therefore the total number of particles, is not conserved. And in our context, the important consequence of that is that quantities such as this so-called off-diagonal expectation value, that is the expectation value of two creation or annihilation operators, that can legitimately be non-zero. And so one tends, as a sort of reasonable approximation, which is actually, this is simply the generalization, or the most obvious generalization, to the superconducting state of the standard Hartree-Fock approximation to the normal state. So what we do is to write down an effective Hamiltonian, which contains the one particle terms, and then a so-called mean field term, which does contain Hartree and Fock terms, but these are sort of not relevant to our argument, so I'll leave them out. Then the important part of the mean field Hamiltonian is that we have here an expression which involves these two creation operators and similarly two annihilation operators. And this is multiplied by an expression which we treat as a C number. And this C number expression is given by a formula of this form, with, again, these are these so-called anomalous averages, which can only exist in a situation where you treat the particle number as non-conserved. And again, typically this is what you do in the superconducting state of a fermion, a condensed matter fermion system. You might perhaps, some of you may be rather familiar with the simple case of this procedure, which we get in the standard BCS theory, when in fact this rather messy looking expression just simplifies to something which looks a lot simpler. And here, the quantity delta of R is the quantity we usually call the energy gap, or perhaps better, the off-diagonal field. In some sense, its truer nature is as an off-diagonal field, and that's the role it plays. So, just recapping, the mean field. Sorry, I seem to have got slightly in this. Yeah, okay. So just recapping, the mean field, so-called Bogoliubov-de Gennes Hamiltonian, is schematically of this form. This is a standard one-particle Hamiltonian of the usual type, where we include a chemical potential term so that fixes the average particle number n. Otherwise, the average number tends to be ill-defined. And then we have this, in some sense, the term which is characteristic of a superfluid or superconducting state, where we have these two creation operators, two annihilation operators. So this is now bilinear in the annihilation and creation operators. The Hamiltonian does not conserve particle number, that's the whole point of this. However, it does conserve particle number parity. So let's start by considering the even parity terms. Well, it turns out that we can actually minimize this Meanfield Hamiltonian to find the even parity ground state. That's not the important point in the present context. In the present context, the interesting problem is to find the simplest odd parity fermionic states. These are the so-called Bogoliubov quasar particles, which are a generalization of the standard Dirac or Landau particles in the normal state. And for that purpose, we write schematically, following Nambu, and ignoring, I'm going to ignore the spin degree of freedom, it just complicates things. So we write a creation operator for our quasar particle, which has the following interesting form. It's a quantum superposition of a state containing an extra particle here, psi dagger, plus a term which creates an extra hole, or alternatively annihilates a particle. And this, of course, is often written in this standard Nambu form. And then, having written down this general form of your quasar particle operator, you determine the coefficients u and v by solving the so-called Bogoliubov-de Gennes equations, which basically just simply tell you that if we take our Meanfield Hamiltonian, commute it with this operator, we want to get some eigenenergy times this operator. And then we find that the Meanfield Hamiltonian it can be just written in this rather straightforward form. All this is very standard textbook stuff. If I could get this to... okay. Okay, so... Oh, help. This does not seem to be advancing in the way I want it to. I want to go to the next slide, please. Sorry. Yeah, fine. So, okay, fine. So all of this is quite standard textbook stuff. Now, but the important point I want you to note is that in the mean field treatment, fermionic quasar particles in a superconductor or Fermi superfluid are supposed to be quantum superpositions of particle and hole. And therefore, they don't correspond to a definite particle number in your system. And this is justified, typically in the literature, by appeal to the notion of spontaneously broken U1 gauge symmetry. And this particle-hole mixing is sometimes, in my opinion misleadingly, regarded as analogous to the mixing of different bands in an insulator by spin-orbit coupling. And as many of you might know, when you get under certain circumstances, when you get mixing of different bands by spin-orbit coupling, that is when you get a so-called topological insulator, and these things have been a subject of enormous interest in condensed matter physics in the last few years. So people often make then an analogy between these so-called topological insulators and topological superconductors, which we'll come to in a moment. Okay, so just to recap, in general, fermionic Bogoliubov quasar particles are created by this kind of operator, linear superposition of particle and a whole, with the coefficients given by the solution of the BTG equation. Just repeat. So now the interesting question is, do there arise solutions of the Bogoliubov-Dijen equations such that the creation operator is indeed its own Hermitian conjugate, and therefore the energy of such a particle is automatically zero? In other words, do we find particles in condensed matter physics which, crudely speaking, correspond to the idea of a Majorana in particle physics? And it turns out the answer is yes, but it requires several things to be right. First of all, the spin structure of the U and V coefficients must be the same. In other words, you must get pairing of parallel spins, not as in BCS, simple S-wave pairing of parallel spins. But, okay, but there are systems in which this happens, and we'll come to a few of them. Secondly, it must be the case that for the solution of your Bogoliubov-Dijen equations, you have this relation between the U and V components. This is the particle amplitude and the whole amplitude. If that's not enough, it turns out that to really get these things to exist, you need some interesting structure of your generalized gap function. For example, the so-called P plus IP scheme, in which the effective field, the generalized effective field, off-diagonal field, has, crudely speaking, the form of something rather boring, depending on the center of mass. Then you have some kind of internal wave function of your Cooper pairs. Now, remember that in a standard BCS S-wave superconductor, this would just be, the internal structure of your Cooper pairs is really rather boring. It's totally isotropic. It depends only on the distance they are apart. In a P plus IP, a so-called P plus IP Fermi superfluid, like, for example, the A phase of liquid helium-3, crudely speaking, the wave function corresponds to your two fermions circling around one another with angular momentum 1. That's a possibly misleading description, but I think it's a useful intuition of what's going on there. Anyway, you need something which has this kind of extra degree of freedom occurring here. Now, why? Okay. A case of particular interest, at least historically, has been the case of so-called half-quantum vortices in strontium ruthenate. The point about strontium ruthenate is that it's a rare example of a superconductor which is believed to have the so-called P plus IP structure of its pairing. We're not absolutely sure that that's so, but most of the evidence does seem to point to that identification. And it turns out that you can make a peculiar type of vortex. Remember that if it's odd parity, if this is odd real parity in real space we're talking about now, if it's P plus IP, then it's odd parity in real space, that means you have to get parallel rather than anti-parallel spins paired. And so if you've got up spins paired and down spin pairs, then what you can do is to make a so-called half-quantum vortex, in which you make a regular Abrikosov-like vortex in, say, the up spins and nothing in the down spins. And when you do that, it turns out that you can get Majorana fermion-like states sitting on these half-quantum vortices. And notice, incidentally, that either you have two possible situations. Either you have an even number of vortices, in which case you can, in principle, get a Majorana fermion, a number of Majorana fermions sitting on it, or if you don't, then it turns out that your boundary, the boundary of your system, in some sense is rather like a delocalized vortex and has the same properties. That will be important later. Now, why are these Majoranas of special interest? Well, I think the thing which has really excited the major interest in these beasts is the possibility of using them for topological quantum computing. In other words, as most of you know, the idea is that you may be able to carry out your quantum computing in such a way that the system is protected against decoherence by, in some sense, the complexity and entanglement of your many-body wave functions. And so Majorana fermion, the use of Majorana fermions is a particularly direct and dramatic way of trying to implement this kind of situation. So why are these beasts so useful, or thought to be so useful, for topological quantum computing? Well, first of all, a Majorana fermion, at least within the mean field theory, is an exactly equal superposition of an extra particle and an extra hole. And therefore, well, not just therefore, there's a little more argument, but because of this, it is protected against being detectable by any kind of local probe. The second point is that under braiding, again in the mean field theory, it's believed that Majorana fermions should behave as Ising anyons. If we have, suppose we have two of these half quantum vortices and there's no Majorans around, we just have these vortices. If we then interchange these vortices, then our many-body wave function presumably just picks up a trivial phase, basically zero. If, on the other hand, we have two Majoranas sitting on these two vortices, one on each vortex, and we interchange them, then it turns out, at least according to the standard arguments given by Ivanov, this guy here, it turns out that we pick up a phase of pi over 2. Now, remember that if you were just to interchange two ordinary fermions, then you get a phase of pi. So this is different. You're getting a pi over 2. And then it turns out that once you've got that fundamental feature, then it turns out that these Majorana fermions behave under braiding as so-called Ising anyons, and that then permits at least a partially protected, topologically protected quantum computer. Sorry? No, not a forward. No, absolutely not. No, it turns out that the problem is that you can do two particle operations in a very nicely topologically protected way. You can't do one particle operations, and for that you need even more curious beasts, the so-called Fibonacci anyons. But I won't talk about those. So so in principle, what you do, crudely speaking, is this: you try to create pairs of half quantum vortices with or without Majorana fermions sitting on them. The ways of trying to do that: you braid them adiabatically, and finally you recombine and measure the result, and that process is at least partially topologically protected. So that's been a major cause of excitement in the field in the last few years. Now let me first make a few comments on the Majorana fermion idea, sorry, typo here obviously, within the standard mean field approach. And the first question, which has sort of bugged me ever since I first learned about these exotic beasts, is what exactly is a Majorana fermion? And I think to see the answer to that, what we have to do is to recall that it has energy exactly zero, so that its creation operator, gamma dagger I, simply commutes with the Hamiltonian. It gives you that. Now, that equation actually has not one, but two possible interpretations. First of all, gamma dagger I creates a fermionic quasi-particle with exactly zero energy. If that's the case, then what that means is that the odd parity ground state, odd number parity ground state, is exactly degenerate with the even number parity one. And that's in some sense, the point which has been mostly focused on in the literature. On the other hand, there is a trivial alternative interpretation of this statement, namely that the operator gamma dagger I simply annihilates the even parity ground state. In other words, it's what I call a pure annihilator. However, it's very easy to show that in neither of these two cases individually do we have the crucial situation that gamma I is its own Hermitian conjugate. To get that, what we have to do is to superpose these cases A and B. In other words, a Majorana fermion, mysterious as it seems, is actually simply a quantum superposition of a real Bogoliubov quasi-particle and a pure annihilator. that, in some sense, that point has been made backwards in the literature, but I don't think it's very often been made forwards. Related to this is the point that Majorana solutions always come in pairs, and therefore by superposing two Majorana fermions, we can make a real zero-energy fermionic quasi-particle. So you have now a Majorana sitting, let us say, on a half-quantum vortex here, and a second Majorana sitting on a second half-quantum vortex over here. You put them together in this way, and lo and behold, out comes a single zero-energy Bogoliubov quasi-particle. Okay. Now, the curious and fascinating point is that this extra fermion is actually split between two regions which may be arbitrarily far apart. In other words, this vortex, you can take this vortex off to the end of the room, and this one off here, and you still have only a single fermionic quasi-particle sitting on these two vortices, which at first sight is very mysterious because, after all, well, I mean, if you just had two ordinary simple quantum wells, you'd expect to get two possible quasi-particle states corresponding to an even parity, even spatial parity, and an odd parity, spatial parity situation. So I think personally that it's much simpler to think of this whole business by not mentioning Majorana fermions explicitly at all, but rather by thinking in terms of these extra fermions. And then, so for example, if I, in this language, if I interchange two vortices, each carrying a Majorana fermion, that's equivalent to rotating, as it were, a single Bogoliubov fermion, which is sitting on both of those vortices. And then the statement is that when you rotate that zero-energy fermion by pi, and thereby, according to Ivanov's calculation, you pick up a phase change of pi over 2. Which interestingly, this is probably not significant, but interestingly, if you work out what would happen if you had the usual situation with two real potential wells and a particle which could be in an even or an odd parity state, the first one, sorry, good, thank you, that's fine, 10 minutes, yep. Then it's the average of the phase which will be picked up by a symmetric and an antisymmetric state. I think it's a very nice implementation of the idea of a Majorana fermion, which I think helps one's intuition a lot, is the so-called Katai quantum wire. This is a nice system which was introduced by Katai about 15 years ago now, and basically it consists of a whole lot of sites and a set of fermions on them, which can either hop individually from one site to the other, or in some sense hop in pairs from one side, corresponding to the off-diagonal terms in the Hamiltonian. Now, I won't go through the algebra, but it turns out that the fermionic excitations for this kind of system have this structure here, so they are properties not of a single site, but on two neighboring sites, or if you like, the links between the sites. And the energy for the I-1 site is some number xi. You can work all that out, but I won't go through the details here. But here's the interesting point. You start off with links of arbitrary strength between the sites, and you get nice localized fermionic quasi-particles corresponding to the different links here. Then you gradually weaken one of the x on one of the sides so as to turn down, as it were, the strength of that link to 0. Now what you've got is you've got a fermionic quasi-particle sitting on this link here, but its energy is exactly 0. In other words, putting in one extra fermion on this side just doesn't change the many-body energy. Finally, you decouple these, you break this ring apart to this situation here. What's happened to the fermion which was sitting on this link? Well, clearly, by symmetry, it's got to be shared between the ends of the line here. And that's what you find. You find you have one Majorana fermion sitting here, one sitting here, and lo and behold, they have all the nice properties that you were told. So that's a very nice example. Second set of comments, the experimental situation. In strontium ruthenate, there is evidence for half-quantum vortices. That's the work of my colleague Rafi Badakian at UIUC a few years ago. None so far for Majorana fermions. Helium-3b, there's circumstantial evidence from ultrasonic attenuation that you may get Majoranas sitting on the walls. Helium-3A, as far as I know, no evidence so far either way. No evidence for half-quantum vortices either in helium-3A. Now, an alternative proposed setup, which has been widely studied in the last 5 years or so, and this is a very, very schematic version, is that you basically have a quasi-one-dimensional semiconducting wire, in parts of which you induce superconductivity by a proximity effect. And then it turns out that the superconductivity, and you have a strong spin-orbit interaction in this wire. And then it turns out that basically the situation is rather similar to what it is in a P plus IP superfluid. And what you expect is to Majoranas at these boundaries here. And that's what people look for experimentally. And what they usually look for is a zero bias anomaly in the current voltage characteristics. First experiment was done by the Delft group, Murik et al. In 2012, and there have been several subsequent experiments. Now, the interesting point is that the theory does make rather precise predictions on the magnetic field, the dependence of these IV characteristics on magnetic field, on the S-wave gap in your bulk superconductor, on the temperature, etc., etc. And these do seem to be coming out roughly right. Trouble is that the argument in such a case is always, crudely speaking, what else could it be? And the answer is, unfortunately, quite a lot of other things. There have been various other proposals in the literature for the interpretation of these experiments. So it really isn't terribly clear. Very quickly, the second possibility is a Josephson circuit involving a P plus I, P wave-like superconductor, and the theoretical prediction, which has been made by many people now, is you get a so-called 4-pi periodicity in the current phase relation, instead of the normal 2-pi. Trouble is that any parasitic one-particle effects can mimic that. It's basically the Byers-Yang theorem, that and any odd one-particle effects will tend to mimic it and have nothing to do with Majoranas. Finally, there's one possible smoking gun, which people have not explored a lot so far. That's the idea of teleportation. If you really got a single fermion, which is split between these two very distant sites, then, at least at first sight, there are intuitive arguments which say, if I try to introduce an extra electron into this site here, then something may pop out instantaneously, or quasi-instantaneously over here, at a speed much faster than the sort of typical velocities of the system. Now, it would be nice to look for that, and it would really, I think, be a smoking gun for Majoranas. Problem is that the theorists simply can't agree among themselves as to whether this effect exists or not, which to my mind is something of an embarrassment, actually, but they certainly don't seem to be able to. Finally, in the last 5 minutes or so, I assume I have 5 minutes still, let me just talk a little about what happens if you try to go beyond the mean field approach. We actually have a problem. The whole apparatus of mean field theory rests fundamentally on the notion of spontaneously broken U1 gauge symmetry. In other words, the idea that you can write your ground state in this form here, and therefore that you can write your quasi-particle, your fermionic quasi-particle operators in this form here. Now, I'm aware that this audience absolutely certainly is very keen, as I would be, on the idea of spontaneously broken U1 symmetry in particle physics. Unfortunately, condensed matter physics, despite what you may have been told in many books and review articles and by some distinguished speakers, spontaneously broken U1 symmetry is a myth, period. It simply does not occur. And if anyone wants to ask me about that in question time, I'm very happy to discuss it. Now, that doesn't matter for the even parity ground state, because by this trick invented by Anderson many years ago, you can basically recover a particle number conserving state by this trick here. The odd parity state, this equation is actually fatally wrong. And there are some rather straightforward ways of illustrating this, actually. It turns out that there are rather simple arguments based on Galilean invariance, which shows it has to be wrong. Similarly, there's a famous recent case concerning the NMR of this alleged surface Majorana fermion in the B phase of helium-3. Again, if you use mean field, you get that completely wrong, and one can demonstrate this quite explicitly. So, what do we do? What we have to do is to replace our quasi-particle creation operator, gamma delta, by the following. It is indeed a quantum superposition of an extra real particle here, an extra electron, and an extra hole, but when you create that hole, you must conserve particle number by creating an extra Cooper pair to go with it. Now, how come that we could have got away with this for 50 years? How come that all these textbook arguments based on the standard mean field approach seem to give roughly the right answer? The answer is that so long as the Cooper pairs have no particularly interesting properties, that is, no linear momentum, no spin, no partial localization or whatever, then it doesn't really hurt. That extra Cooper pair just runs away to infinity and gets lost, and you forget about it. Problem is that to generate Majorana fermions, the pairs must have interesting properties. In particular, they must have at least apparently an intrinsic angular momentum. And this really totally changes the situation. It doesn't change, at least to my knowledge, it doesn't change the arguments about the existence of Majorana fermions. They still exist. But it does, I believe, completely change arguments about their braiding, their undetectability, and so on and so forth. And this is what my student, Yuzhou Lin, and I've been looking at for the last couple of years or so. In other words, we need, in fact, a completely new approach to this problem, and I anticipate that at least some of the standard results about topological quantum computing are going to have to be radically modified in the light of this business. So, so anyway, that's my story, and hopefully, if you have questions, we have a little time for them. Thank you. I think I have a question.
Thank you very much, Anton. We have time for some question.
David has a question.
So this last bit reminds me of tea at Princeton.
Of who, sorry?
Having tea at Princeton,
yep.
Where I remember violent arguments between Eugene Wigner and Phil Anderson.
Oh, yes, yes.
As to whether, BCS theory of superconductivity, whether there really is spontaneous symmetry breaking. Mm-hmm. And you know who took which side.
Sure, of course. Yes,
now, I always thought the answer was that for n equals infinity, there's no problem.
But it never is equal to infinity.
No, I know. But when n... so, we have no problem in particle physics with spontaneous breaking of a U1 gauge symmetry.
Yeah.
But we always work, for us, n is equal to infinity. Mm-hmm. But Eugene Wigner would always argue, as you just said, n is always finite in any real system, and therefore it makes no sense. Bum, 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 bum. And Phil would explain to him in a way that nobody could understand why it made sense. Now, but that would lead me to suspect that this concern of yours is negligible in the thermodynamic limit, and the volume goes to infinity, and the n goes to infinity limit.
No, I don't believe it is. No,
it isn't.
No, not at all.
So you think these are of order 1 effects?
Yep. At least in certain geometries, in certain situations.
Thank you. Another question?
People who are trying to check whether these Majoranas are really Majoranas, right, are trying to do interference.
They would,
And you would say that, well, I suppose if they saw the I, the e to the I pi over 2, you would say, okay, well, this effect is not important.
If they saw exactly I pi over 2, yes.
I see.
There's a slight sort of experimental problem here, in that at least right now we seem to be finding that it isn't I pi over 2 exactly. It's I pi over 2 plus something which is exponentially small, but not the exponent is not anything connected with the distance apart of the Majorana. It's something more intrinsic.
Exponentially small.
Well, what? It's something like the Fermi energy divided by the gap, which has nothing, which is a bulk property, which has really nothing to do with Majoranas.
I see.
Thank you. I think that there are no more questions, and I would like to thank you, Anthony, for this very, very nice talk. Yeah, beautiful.
Thank you.